Complex numbers. Complex numbers are an extension of real numbers, typically written in the form a plus b times I, where a and b are real numbers and I is the imaginary unit, such that I squared equals -1. We can visualize them using the complex plane, a graphical representation that extends the real number line into two dimensions, one representing the real axis and the other being the imaginary axis. Initially, complex numbers were met with resistance in the mathematics community because they defied the intuition that the square of a number must always be non-negative. Over time, complex numbers have proven indispensable for modeling various phenomena, with applications in fields such as signal processing, electrical engineering, and quantum mechanics, where they are used to describe waveforms, oscillations, and other dynamic systems. Complex analysis, the study of complex functions, provides powerful insights and tools not available in real analysis, such as contour integration and the use of residues, which can simplify problems in ways that real-valued functions cannot. As a result, many mathematicians consider complex analysis to be a more elegant or complete framework than real analysis, as it allows for a more unified treatment of functions and operations. Complex numbers are also present in Euler's formula, famous for being considered the most beautiful equation in mathematics. Raising Euler's number to pi times the imaginary unit results in -1. For that reason, complex exponentiation is very useful in describing rotations on the complex plane. Quaternions. Now that we defined a number system with 2 dimensions, what happens if we try to construct one with 3? This is what Irish mathematician William Rowan Hamilton tried with no success, until arriving at a coherent system with not 3, but 4 dimensions in 1843. These are called the Quaternions. They are numbers on the form a plus b times I plus c times j plus d times k, where these coefficients are real numbers and both I, j, and k squared are equal to -1. For number systems like these, multiplication tables can be used to define the relationship between basis numbers. One interesting feature of the Quaternions is the lack of commutativity of multiplication. That is, 2 numbers multiplied do not always result in the same product if we change their order. While it seems like an undesirable property, it is actually very useful in representing rotations of bodies in 3 dimensions, since this behavior also exhibits lack of commutativity. For that reason, they ended up being widely used in computer graphics, robotics, and physics. Quaternions also give interesting insights into 3-dimensional vectors in general, as seen in the definition of the cross product. Cayley-Dickson construction. After quaternions, it's possible to define an 8-dimensional number system called octonions. They have 7 different imaginary units that equal -1 when squared. Their multiplication can be summarized using this structure called a phanoplane. It's possible to keep generating new hypercomplex number systems using the so-called Cayley-Dickson construction, named after Arthur Cayley and Leonard Eugene Dickson. This method takes some number system and produces another with twice the number of dimensions, with well-defined multiplication rules. This gives rise to setinions, trigintaduonions, and many others. A downside of this construction, however, is the progressive loss of interesting arithmetical properties. Octonions, for example, lose the associative property of multiplication. Setinions lose the alternative property while also containing 0 divisors, which means that when the product of 2 numbers equals 0, it doesn't necessarily follow that one of the factors is 0. As the number of dimensions grow, these numbers become more and more convoluted and are not well studied or applied in general. Split complex numbers. Just like how I was defined to be the solution to this equation, which had no answer in the real numbers, James Cockle defined j in 1848 to be the solution to 1 plus square root of j equals 0. Originally, it was intended to be a number whose square root is -1. However, its meaning changed throughout history. Nowadays, it is simply considered to be the solution to the equation j squared equals 1, where j isn't 1 or -1. Split complex numbers, then, are numbers of the form a plus b times j, where a and b are real numbers. It might have started as an attempt to provide a solution to an impossible equation, but now that its meaning has changed, it might seem like an even more made-up system than complex numbers that nobody was really asking for. Regardless, they prove to be useful in some applications, such as representations of hyperbolic rotations in Lorentz boosts, which are very common in special relativity. Let's take a look at some interesting properties. If multiplying by I rotates a number 90 degrees around the origin on the complex plane, multiplication by j flips the horizontal and vertical axis. You can check that's true applying the rules of multiplication. Another interesting parallel is the exponential function. E to the power of I times x results in a circle traced around the origin where the resulting number can be calculated by using trigonometric functions. This comes directly from the Taylor expansion of the exponential function that can be divided into the real part that equals a cosine function and the imaginary part that equals a sine function. Something similar happens with e to the power of j times x. Since there are no alternating positive and negative terms like in the complex case, this expression can be split into the hyperbolic cosine function and the split complex unit times the hyperbolic sine function. The resulting shape traced by the exponential function is a hyperbola. For this reason, split complex numbers are also called hyperbolic numbers. Other interesting features include the possibility of defining imaginary modulus, the existence of zero divisors, and of idempotent elements, that is, elements that when squared result in themselves. These can even be used to define an isomorphism between this system and the direct sum of real numbers, where both multiplication and addition are defined component-wise. Multicomplex numbers. One problem with split complex numbers is that there is no root of -1 anymore, so we are back at having an incomplete number system. But actually, at the same time split complex numbers were introduced, a four-dimensional number system known as tessarines was defined. It consists of two basis elements, complex I and split complex j, and a third one equal to their product, which equals -1 when squared, like a second imaginary unit. Tessarines are isomorphic to another system known as bicomplex numbers, so let's take a look at them. Bicomplex numbers are numbers on the form z1 plus z2 times I2, where I2 squared equals -1, but instead of z1 and z2 being real numbers, they are actually complex numbers. It's called a tensor product. It's like a complex number inside another complex number. Both z1 and z2 have an imaginary unit I1, different from I2, where both of them commute. If we expand this definition, we can see all of its four dimensions. The fourth dimension is the axis related to the product of both imaginary units. And because they commute, this last unit is actually analogous to a split complex one. It squares to +1. This number system is associative and, unlike Quaternions, commutative. However, unlike Quaternions, they do not form a division algebra, since they have zero divisors just like split complex numbers. Here are some other isomorphic systems that can be made depending on what you choose to make the tensor product of. They all have the same structure, two imaginary units and one hyperbolic unit. Just like how split complexes are isomorphic to the direct sum of reals, all of these systems are isomorphic to the direct sum of complex numbers, and we can make a similar isomorphism from the one we did before, resulting in a system composed of two complex numbers where addition and multiplication happen element-wise. We can generalize this by making the tensor products of complex numbers multiple times. Those are called multicomplex numbers. They are always commutative and associative, which are interesting properties that the Cayley-Dickson numbers do not have. If we use split complex numbers instead, we arrive at similar systems that never get an imaginary unit. These are called multi-hyperbolic numbers and have similar properties. Modified Cayley-Dickson construction. We have already seen one way to generate number systems with more and more dimensions through the standard Cayley-Dickson process. If we modify it a little bit, we arrive at the modified Cayley-Dickson construction. That's a systematic way of generating even newer number systems that contain both imaginary and split complex units. Let's take a look at some of them. Applying this process to real numbers, we get split complexes. Applying again, we arrive at the split quaternions. They are associative but not commutative, just like quaternions. Since they have hyperbolic units, they have zero divisors and do not form a division algebra. An interesting fact about them is that they are isomorphic to the set of 2x2 real matrices. This means that we can define a mapping between them so that each 2x2 real matrix has a corresponding split quaternion number, and the structure of operations such as addition and multiplication is preserved. Another interesting feature is the presence of nilpotent elements. These are numbers that equal 0 when squared but aren't 0 themselves. At the next level, we arrive at split octonions. They are not associative nor commutative and not a division algebra. Associative algebras in general have an interesting property. They can be represented as matrices. Here are some ways of representing some hypercomplex numbers as real matrices. Octonions, since they aren't associative, don't have this property. Split octonions, however, despite still not being associative, can be represented by structures known as Zorn matrices. They are like matrices, but they have vector entries and their own kind of multiplication. Numbers generated from the modified Cayley-Dickson construction, instead of having only imaginary basis like in the standard construction, have half of its basis being hyperbolic while the rest is imaginary. Dual numbers. Remember nilpotent elements we found in split quaternions? We can define a two-dimensional number system with those. They are called dual numbers, and the nilpotent element, meaning the number equal to 0 when squared, is usually represented as the Greek letter epsilon. Clearly, this system has 0 divisors, which the main one is epsilon itself. Because of that, division by epsilon is not well defined. What about exponentials? Let's apply the same logic we used when defining split complex exponentiation. We can expand e to the power of epsilon times x into this infinite sum. However, since epsilon squared is 0, most terms do not contribute to the sum. We end up with only those two terms, resulting in 1 plus epsilon times x. Plotting this result on a graph, we can see that the dual exponential looks like a straight vertical line passing through 1, while its mirror image passes through -1. We can try describing it using some kinds of trigonometric functions, just like we did for these other systems. Like we've just seen, the even terms would represent some kind of cosine, while the odd terms would represent some kind of sine. These are actually called Galilean trigonometric functions, and they are pretty trivial. Galilean cosine is identically equal to 1, while the Galilean sine of x is just x. These names make reference to Galilean relativity, which is one application of dual numbers. It is a classical physical model of spacetime that predates Einstein's relativity. They can also be used in programming to compute derivatives of functions with a method called automatic differentiation. However, just like the split complexes, they do not have a root of -1, so they are pretty incomplete. We can take tensor products with any of these and define even more exotic number systems that keep commutativity and associativity. Generalized complex numbers. So far, we have seen 3 different types of two-dimensional number systems. Complex numbers that feature a constant that equals -1 when squared, split complex numbers that feature a constant that equals 1 when squared, and dual numbers that feature a constant that equals 0 when squared. But what if we want to generalize this to any real number? What about some constant that equals -2 when squared, or 9? Or what about a constant that equals itself when squared? All of those are considered generalized complex numbers. They are numbers on the form a plus bx, where a and b are real numbers, and x is some new constant that equals x cubed plus p when squared. It might look like we have created a huge amount of new number systems, but if we take a closer look, we will notice that they are actually the same as these ones we have already seen before. Let's take a look at x squared equals -2, for example. This number behaves just like square root of 2i. It's just the same as the complex numbers all over again. What about x squared equals 9? It's the same as 3j, so this one is isomorphic to split complexes. This one is a little trickier. What about x squared equals x? We can remember one of the properties of split complex numbers, the presence of idempotent elements. X can just be understood as 1/2 plus 1/2 j, since they behave in the same way. In general, it has been proven that any number system on this form is actually isomorphic to these 3 previously seen systems. This diagram shows what each definition for x is actually isomorphic to. The horizontal axis represents the coefficient, while the vertical axis represents the independent element. These points represent the canonical complex numbers, split complex numbers, and dual numbers respectively. Anything on this green line is isomorphic to dual numbers. For example, the system formed by a plus bx where x squared equals 2x minus 1. X behaves the same way as 1 plus epsilon, so we can easily define a mapping between both systems. Anything on the top of this parabola is isomorphic to split complexes, while anything on the bottom behaves the same way as the complex numbers. In some sense, we can say that we have completely classified all two-dimensional number systems. Clifford algebras. It can be a little complicated to define them formally, but they are a system generated by some basis vectors and a function that defines what happens when you square them. In a simple context, we can think of them as a number system where there are basis vectors that square to either -1, 1, or 0. These basis vectors can be multiplied to form new units, so an n number of basis vectors will result in a 2 to the power of n dimensional number system. These basis vectors also end up being anti-commutative, that is, changing their order changes their sign. Choosing the real numbers as their underlying field, we can represent different Clifford algebras in this way, where p is the number of basis vectors that square to 1, q to -1, and r to 0. This other form is actually more common, with no nilpotent basis vectors. Some number systems that we have seen are actually types of Clifford algebras, such as complex, split complex, and dual numbers, quaternions, and split quaternions. Although some systems generated by the Cayley-Dickson construction have isomorphic analogues here, octonions and higher numbers can't be expressed as Clifford algebras since they aren't associative. The next step in this sequence would actually be isomorphic to a system called split biquaternions, which is isomorphic to the direct sum of quaternions or the tensor product between quaternions and split complex numbers. Clifford algebras also exhibit another interesting behavior. There is a pattern that shows up when dealing with higher dimensional systems composed of basis units that square to 1 or -1. If adding 1 to q means moving clockwise and adding 1 to p means moving counterclockwise, this diagram shows what each system is isomorphic to in terms of matrices. Simple systems end up being isomorphic to trivial 1-by-1 matrices, which behave just like the number systems themselves. However, this one is isomorphic to 2-by-2 real matrices, for example, which is actually also isomorphic to split quaternions. And this thing is isomorphic to the direct sum of 4-by-4 quaternion matrices. Since this diagram is circular, the pattern repeats after 8 turns. This pattern is called Bott periodicity, a result from topology. Quotient rings. That's one way to generalize many of the hypercomplex number systems we have seen so far. Studied in ring theory, quotient rings of real numbers work by adjoining some variables to the reals, such as x. Then we take the quotient by an expression called an ideal, such as x squared plus 1. By doing this, we are considering that any multiple of this expression will be equivalent to 0. If that's the case, then we can find that x squared should be equal to -1, which means x behaves the same way as complex I in this context. Therefore, this quotient ring is isomorphic to the complex numbers. The other two-dimensional numbers can also easily be defined this way, even the generalized complex numbers. Quaternions can also be described using quotient rings. However, we need two variables and these expressions. This way, we can see that x and y both equal to -1 when squared, and their product is anti-commutative, just like the quaternions. We can find isomorphisms of tensor products by factoring the ideals. For example, since x squared minus 1 factors into x plus 1 times x minus 1, this shows that the split complex numbers are isomorphic to the direct sum of reals. We could find quotient rings that are isomorphic to bicomplex numbers by finding polynomials that factor into two irreducible polynomials over reals. We've seen that two-dimensional systems can be made with ideals containing a one-variable second-degree polynomial, and four-dimensional ones with ideals containing a one-variable fourth-degree polynomial or two-variable second-degree polynomial. Would that mean that three-dimensional one could be defined using a third-degree polynomial as an ideal? After everything we have studied, we haven't found a single number system that does not have a power of 2 number of dimensions. That's why Hamilton found the Quaternions but not Ternions in the first place. So what's the matter? Why do people say there are no 3-dimensional hypercomplex number systems? As it turns out, the problem with trying to define 3-dimensional number systems is that they will not have interesting properties, such as absence of zero divisors. But at this point, we have seen so many kinds of numbers that also don't have this property, so why deny these new ones? So here are the only 4 3-dimensional number systems that we can define using a third-degree polynomial as an ideal, up to isomorphism. And here are their multiplication tables. We can see that we have hypercomplex units as results of squaring other units instead of real numbers like we are used to. But that's not too much different from what we have seen with the generalized complex numbers. Since their basis elements are powers of x, they are all commutative and associative, but they all have zero divisors. They are also isomorphic to these. Using quotient rings, we can find hypercomplex number systems of any dimension we want. But wait a second, are they even supposed to be considered numbers at this point? We can define natural numbers, rationals, reals, complex numbers, but there isn't a formal definition for what a number really is. There is no actual place where we draw a line between what is and isn't a number. But maybe that's the spirit of mathematics. We never know the full range of discourse, we just keep exploring whatever new structures we can find and learn whatever there is to learn along the way.